Find path if exists in graph. You got a bidirectional graph with n vertices. Each vertex is labeled from 0 to n-1 inclusive. The edges in the graph are represented by 2D integer array edges, where each edge I equals neighbors, denoting bidirectional edge between vertex and other vertex. Each pair is connected by at most one edge, and no vertex has an edge to itself. You want to find a valid path if it exists from source to destination. So, for example, we want to see if we can go from 0 to 2. And if you have eyes, you can see clearly that 0 goes to 2. But the computer does not have eyes, so we need to explore this somehow. And one way we can do this is for each of these, we want to make a list of their U and V's, the vertex pair. Its edges, vertex is okay. So let's go. So we'll take 0, right, and add it to a map, and we'll have a list of its neighbors. And then we will search if its neighbor is the destination, return true. But what happens if it's more complicated than that? We want to go from 0 to 5. Well, we check 0. We start at 0. We check 1. And then we check 1's neighbors. And if it doesn't have the destination, we should return false. If this was connected, if 1 was connected to 3, we would see if 0 has if any of its neighbors are the destination. If not, then we deepen the recursion and go to 1, check its neighbors. And if 3 was a neighbor, we'd go here. And from there, we would check if one of its neighbors is the destination, which it would be, and it'd be 5. And then you'd return true. So first, we need to make a list of neighbors for each node. List of neighbors for each node. Const. Let's call this graph equals new map. And how do we unpack 2 values inside of a nested array? We can say for let A and B of edges, and then if the graph does not have an entry for the key of A, then graph.set A as the key and the value as an empty list. Do the same for B. And then push B into A's list and push A into B's list. So what you have now is A, and it has B inside of it, the list. And this is, eventually it's going to have like C in it as well. and etc. So it'll grow, right? And so on this side you have B, and it has A inside of it now, which is great. It's what you want. It's what you need. Okay, now search depth first of the neighbors. So we want to see if we've visited something already. We don't want to keep visiting the same stuff. So we're going to have a visited set outside of the recursive function. And then we're going to have the recursive function, which is going to return. So this whole thing, DFS start, we're going to start it from the source. And so now that we know what everything is connected to, and now that we can keep track of if we've seen it before, and we know we're starting from the source, we just need to see if we can go from the source to the destination and see if we can make it from source to destination via neighbors, which we know the neighbors because we have them listed in a graph. Okay, and so function DFS starting from the source, but just a generic parameter node. Okay, so our base case is if we've found the destination. So if the node that we're currently looking at is equal to the destination, then return true. So we're at 0. If 0 was the destination, we'd stop. Otherwise, we're going to add it to the visited and then visit what we haven't visited. So visited dot add the current node, and then let's go through the list of 0's neighbors, which contains 1 and 2. So we need to check the neighbors. So for let neighbor of graph dot get the current node. Now what if 0 was undefined? We'd break our entire program. So we need to say or and then square brackets. So this is valid. We can continue to iterate if there's nothing in empty square brackets, but if this returned undefined, we'd be in trouble. We'd be done for. Okay, so we're going to visit unvisited neighbors and deepen recursion, deepen the call stack. So we're going to depth first search. So we're going to go to 1, and then we're going to try to go to the next neighbor. And if the next neighbor is the 1, then we'll stop, but it's not. And if these aren't connected, then, not good. We backtrack and we go to the other neighbor and try to see if it has neighbors. Which if it did, then we'd continue and we'd find 5. But if it doesn't, which it doesn't, then we would return false. Okay. And so if not visited dot has neighbor, if we haven't visited it, then DFS on the neighbor. Okay, and eventually if we find the destination, we'll return true, and otherwise we can return false for no path found. But what if we do this and we find it early? We're still going to search all the other neighbors. So if one of the recursions finds true, we want to break out sooner than usual. So let's see if this works by itself. So what happened was it will sometimes return false even though one of the recursions was true. So if we find a true recursion, then return true, because it's going to search all possible outcomes, and some of those possible outcomes will be false. So if we find the true one, we want to pass it back up the call stack.